Welcome to this video on MPLS VPN overview. We will cover traditional router-based networks, key aspects of MPLS VPN, terminology, architecture, routing, and label propagation. Traditional router-based networks connect customer sites using dedicated point-to-point links between routers. This approach can be resource-intensive and lack flexibility. Virtual private networks, or VPNs, replace dedicated links with emulated ones, sharing common infrastructure. Customers use VPNs mainly to reduce operational costs. MPLS VPN, or Multi-Protocol Label Switching Virtual Private Network, is a high-performance private networking technology. It uses labels for fast packet forwarding, offering superior quality of service and security, making it ideal for critical data. Key aspects of MPLS VPN include using a service provider's private network instead of the public internet. The architecture involves customer edge, or CE, routers connecting to provider edge, or PE, routers. MPLS VPNs achieve isolation using virtual routing and forwarding, or VRF, which allows overlapping IP addresses. Common types include Layer 3 VPNs for IP routing and Layer 2 VPNs for bridging. Advantages include guaranteed bandwidth and strong security. Let's review some VPN terminology. The provider, or P, device is in the core network with no customer connectivity. The provider edge, or PE, device connects to the customer edge, or CE, devices, which are on the customer side. VPN services are based on two models. Overlay VPNs provide virtual point-to-point links between sites. Peer-to-peer VPNs involve the service provider participating in the customer's routing. This diagram illustrates the various technologies that implement overlay VPNs, such as IP tunneling and traditional Layer 2 VPNs, and peer-to-peer VPNs, which include BGP MPLS VPNs. Overlay VPNs emulate a dedicated leased line. The customer and the service provider do not exchange any Layer 3 routing information. In overlay VPNs, routing protocols run directly between customer routers. The service provider is only responsible for point-to-point transport of customer data, clearly separating responsibilities. This is a connection-oriented protocol. In the peer-to-peer VPN model, routing information is exchanged directly between the customer premises equipment, CPE, and the PE router. This makes adding new sites much simpler, as the service provider SP handles the service provisioning. In the peer-to-peer model, the PE routers exchange customer routes through the core network. These customer routes are then propagated to other CE routers. The MPLS VPN architecture combines the best features of both overlay and peer-to-peer VPNs. PE routers participate in customer routing for optimal routing and easy provisioning. They also maintain separate routes for each customer, allowing overlapping addresses. This diagram illustrates the terminology within the MPLS VPN architecture, showing how different customer sites connect to the P network via PE routers. The PE router architecture is similar to the dedicated PE router peer-to-peer model. However, dedicated per-customer routers are implemented as virtual routing tables within the single PE router, including the global IP routing table for the backbone. Routing information propagation across the P network involves different interior gateway protocols, or IGPs, for various customers being managed by the PE and P routers. A dedicated routing protocol is used to carry customer routes between the PE routers across the P network. This flow shows the dedicated routing protocol carrying customer routes from PE router X across the P network to PE router Y. A 64-bit route distinguisher, RD, is prepended to an IPv4 address to make it globally unique, resulting in a VPNv4 address. VPNv4 addresses are exchanged between PE routers using multi-protocol BGP or MPBGP. This diagram visually represents how the route distinguisher is used to differentiate between potentially overlapping IPv4 addresses from different customers, ensuring global uniqueness as VPNv4 addresses. The route distinguisher combines with the IPv4 prefix to form the VPNv4 prefix, which is essential for carrying customer routes across the shared backbone. The route distinguisher ensures that even if two customers use the same internal IPv4 address range, the PE routers can distinguish between them based on the unique VPNv4 prefix. The RD itself has no special meaning and is used only to make potentially overlapping IPv4 addresses globally unique. While it could serve as a VPN identifier, This design cannot support all necessary customer topologies. From the CE router's perspective in MPLS VPN routing, it runs standard IP routing software and exchanges updates with the PE router, appearing as just another router in the customer network. Various routing protocols are supported. From the overall customer perspective, the PE routers appear as core routers connected by a BGP backbone, following standard BGP and IGP design rules. The P routers are hidden from the customer. From the P router's perspective, they do not participate in MPLS VPN routing and do not carry VPN routes. P routers run the core IGP, exchanging information about global subnets, such as core links and loopbacks, with the PE routers. PE routers exchange VPN routes with CE routers using per-VPN routing protocols. They exchange core routes with P routers and other PE routers via core IGP, and exchange VPN v4 routes with other PE routers using MPI-BGP sessions. PE routers maintain a global routing table for core and internet routes. They also have VRF tables for different customers, filled with information from CE routers and MPBGP updates from other PE routers. For VPN packet forwarding, PE routers label packets with a label stack, including the LDP label for the egress PE router, and forward them across the MPLS backbone. P routers perform label switching, and the egress PE router forwards the packet to the CE router. VPN label propagation is essential. The egress PE router assigns a VPN label to every VPN route and advertises it to all other PE routers in an MPBGP update. A label stack is then built in the VRF table. To reiterate, the VPN label is assigned by the egress PE router for each VPN route and distributed to all other PE routers through an MPBGP update. Overlay VPNs are suitable for small-scale implementations and offer strong isolation. Peer-to-peer VPNs guarantee optimum routing and are more scalable for larger deployments, with easier site provisioning, since only the sites, not the links, are provisioned. Drawbacks of overlay VPNs include requiring a full mesh of manually provisioned virtual circuits for optimal routing and encapsulation overhead. Peer-to-peer VPN drawbacks include the service provider participating in customer routing and carrying all customer routes, requiring deep IP routing knowledge. Thank you for watching this video. Please subscribe for more updates.